for today. So yeah, we go into chapter 6. We start talking about protection, right? Different kinds. You guys able to see that okay?
Yeah, I can see it.
Yeah.
Yeah, this is a video. They do like a lab demo, but it's a video by Eaton. Eaton does a lot of, they manufacture a lot of these products like circuit breakers and stuff like that. So a lot of the installs, you pull them out and you're pulling out Eaton boxes, EATON. They got one, what is it? One really big facility right down in, like in the north of Arkansas. I had a buddy go down there. He got relocated and yeah, he worked for a big old plant down in Eaton. I guess he likes it, but anyway. But no, this one's an actual video by Eaton. Let's make sure.
Today we'll be talking about the developments in circuit breaker technology and how they can protect homes from one of the leading causes of household fires. Early residential electrical circuits were typically protected by fuses. When the circuit saw too much current, the metal strip in the fuse would melt apart or blow due to the heat generated. Of course, each time this happened, it had to be replaced. In 1936, Westinghouse unveiled the first residential circuit breakers. These breakers soon became the standard protection in residential wirings, replacing fuses with a more reusable design. Their operation was simple: monitor the circuit for excess current. Today, the same technology is still in use, but with a few improvements to help with better performance and quality. Now, there are two events which the standard thermal magnetic breaker protects against: overloads and short circuits. An overload is where a circuit is pulling too much current and could potentially overheat and damage the wiring. This is often seen where too many devices are plugged into one outlet or on the same circuit. Once the breaker senses this overload, it trips, protecting the circuit from causing damage. It does this by way of an engineered bimetal that bends when current above its rating is applied across the circuit. It would only take a few seconds to trip the breaker if a high amount of excess current is being pulled through the circuit, but it could take several minutes if the current is just above the breaker's rating. Another condition that the standard breaker protects against is a short circuit. This is when the hot conductor comes in contact with the ground or neutral conductor. The resulting short circuit creates a spark or arc that often damages one or both of the circuit components. On a typical 20 amp breaker, a short circuit will increase the amount of electrical current, starting at 10 to 20 times its normal load, and can go as high as the full current rating of the breaker. Protection from short circuits is provided by means of an electromagnet. When current flows through a circuit, there is an induced magnetic field. Under normal conditions, the magnetic strength is not strong enough to mechanically trip the breaker. However, when a large amount of current passes through the circuit, it significantly increases the magnetic strength and will trip or break the circuit within a fraction of a second. In 1964, Westinghouse introduced the ground fault circuit interrupter, or GFCI. Where a standard thermal magnetic breaker is used to only protect the wire from short circuits and overloads, GFCI breakers protect people and equipment from electrical shocks. These breakers include the standard protection of a thermal magnetic breaker, as well as 5 milliamps of ground fault protection for people, or 30 milliamps of ground fault protection for equipment. A ground fault occurs when the current leaks from the hot wire to a grounded path. These leaks, if left undetected, can lead to equipment damage or cause harm to anything or anyone it comes into contact with. The GFCI breaker measures the amount of current leaving on the hot wire and compares it to the current returning on the neutral wire. If there's any difference, it assumes the missing current has leaked onto the ground wire and trips the circuit. GFCIs are required in bathrooms, kitchens, basements, garages, near swimming pools, and outdoor receptacles. The next type of breaker that was developed for residential applications was the arc fault circuit interrupter, or AFCI. Studies done during the early 1990s showed that a significant amount of residential electrical fires were being caused by a phenomenon called high current arcing. These situations occur when the insulation in the hot wire is compromised and the current is given an arcing path to the ground or neutral wire. Now, the device I have here is designed to recreate this high current arcing fault on a circuit monitored by a typical thermomagnetic breaker. If I cut into the lamp cord quickly, it will create a short circuit, which this breaker will obviously detect. But the conditions leading to a high current arc are much more subtle, not nearly as abrupt as a short circuit. This arcing, which can be in excess of 10,000 degrees Fahrenheit, creates only 75 to 125 amps of overcurrent, not nearly enough to trip the 200 amp short circuit protection of a standard thermomagnetic breaker. Additionally, the arc usually doesn't last long enough to keep the bimetal strip, tripping the breaker on thermal overload. As a result, the arcing fault is more often than not completely undetectable by standard breakers. The branch feeder AFCI was launched around 1994 to provide the overload and short circuit protection, plus protection for the high current arcing where the current exceeds 2 to 3 times the breaker's rating. Internal to the AFCI, a current monitoring circuit board detects any anomalies in the current flow and trips the breaker when a current signature matching an arc is detected. So let's try the same test with an AFCI breaker. As we see, the branch feeder AFCI trips under this circumstance. While this AFCI breaker has been providing fire protection for many years, additional studies have found that another type of arcing also contributes to electrical fires. This arcing condition is called low current arcing and is most common in household cords such as extension cords, appliances, lamps, etc. In this situation, the phase or hot wire is broken, but the two severed ends are still close enough for arcing to occur between them, resulting in the arc actually jumping across the gap. Since this arc is in series with the load, the current will be limited by the loads being drawn. This low current arcing is in the 5 to 10 amp range and won't be detected by the branch feeder AFCI. The combo AFCI was developed to detect this low current arcing. In addition to short circuit, overload, and high current arc fault protection, the combo AFCI provides protection for low current arc faults. As we see, the combo AFCI is able to detect this low current arc fault where any other breaker would fail to respond. The challenge with designing the combo AFCI breaker is that every electrical device will create arcs during their operation. When the contacts close or separate, they create these small arcs, just as I was trying in the demo here. The protective device needs to differentiate between these operational or intentional arcs, such as the flipping of a light switch or operation of a motor, and the non-operational or dangerous arc. The combo AFCI breaker is designed to ride through these operational arcs and only look for sustained low current arcing before tripping. Undoubtedly, you can see why arc faults are some of the most overlooked potential hazards in today's homes. But with Eaton, you can have the silent protection combo arc fault circuit interrupter, as well as peace of mind that your home is safe from these dangers. For Eaton Corporation, I'm Jason Mitzberg. Thank you for joining us today.
Oh, I have my hood on there. Sorry. Yeah, that's the AFCI is the relatively new kid on the block, and thank God. But I mean, and most people don't even realize, you have like these old extension cord or something, or even a relatively new extension cord, but you run over it with a vacuum cleaner, or you got little kids and who knows what they're doing and stuff like that, and people don't check it, and you got these things like laying on your carpet and stuff like that. And so, or even if you're dealing, if you got like an older extension cord or older cords where the insulation's starting to degrade, break down a little, you might have like cracks in it or something like that. And then sometimes if you watch that, you can literally see the little arkings going on across there. And so, then you lay that on something like your carpet or whatnot, and the next thing you know, you've got a house fire. But the AFCI one will protect against that. It actually, like that last one you talked about with the combo, that one actually looks for that, and then because people do stuff, you got like grandma's old vacuum cleaner, where the cord is like older than dirt, and and nobody checks the insulation on it, so it can degrade over time, especially because it's flexible, so it gets a lot of wear and tear on it and this and that, and people continue to use them. They don't think about it, and the next thing you know, yeah, they got a house fire going on, and it's like, oh my God. But that's a cool thing about this chapter we're going into, chapter 6. It looks at, and I mean, look at that, the circuit breaker, right? He said 1936 Westinghouse came out with that, and that's what we're going 80 something years now, 84 years. So yeah, that's quite a long time. And as you've seen by that cutaway, it's an electromechanical, it's basically flexing on that wire mesh inside of there, right? And then it's like a copper. So it looks like if you were to take one apart, that copper that's in there is kind of like a copper braid. And then so what it does is at a certain current, it'll start to pull tight, and then it locks that, it flips that spring. And a fun one with those, did you know that the NEC actually requires a homeowner to once a month, you are supposed to go through every month and exercise the circuit breakers in your panel? So that would mean, flip the main breaker, right? Kill the main power, and then turn on and off every circuit breaker you have on both branches. And you go and ask, and the average homeowner, if they have ever done this, and you got people that have lived in their house for like 20 years and have never done it, but it's electromechanical. So what happens is sometimes those contacts can stick. So even if that copper braid, like say you got a surge or something like that right on the line, and that copper braid's pulling, that thing hasn't been moved in so long that it literally is fused, it's mechanical. That spring over time, if it doesn't get exercised, it could bind up and things like that. But yeah, you are supposed to go through your home panel every month and exercise your circuit breakers, which is a fun one. And then if you even went down your street and asked like a good handful of your neighbors and stuff like that, if they go through and exercise their circuit breakers, they'll probably look at you like you're crazy or something like that. But but you are supposed to. So there's a little tidbit for you, a little extra thing. So anyway, let me get into, where the heck are we? Thing on chapter 6. Yeah, I think it's fun. It's just it's got a lot of different weird little devices and stuff like that. But it's all about circuit interruption and how fast, what kind of, what ways it's looking. As you've seen from that Eaton demo, each one does it a little differently in the way it's monitoring. But yeah, and then let's see. So yeah, we talk about pretty much every type out there, even the plug style. So I mean, the main thing with anything, right? You can't go too far in safety where people's lives are in danger. If it's not properly grounded, you do have a possibility of shock. And why is that? I mean, if you had like see in the old when they first started doing this, if you can get into some of these old homes, their receptacles literally only have two spades, right? Where there is no ground terminal to it. And so what could happen is, I mean, if you were to get some kind of electrical shock, where's that going to go? If it doesn't have a path, it'll try to fly out to the whatever device you have hooked up. Like even to the point where your lamp could become a dangerous thing you don't even realize, and then you go to touch to turn it on, and the next thing you know, you're getting a really good shock. So yeah, this will happen. I mean, everything breaks down. Everything breaks down. Receptacles are not forever. You're actually supposed to go through in your home and periodically update those. You got to remember they're mechanical as well. They got spring tension on where you plug the spades in, and that spring tension over time, with anything, springs tend to give out. So you're supposed to refresh those and update them and this and that. A lot of people don't. You know, they've inherited grandma's house and they haven't changed the electrical since then, and that could be like from before I was even born, like from the 50s or something. You got these old things, and yeah, nothing lasts forever. That's one thing to remember with this stuff. Nothing lasts forever, and like I said, there is no compromise where human life is involved. So one thing you get out of this one, I mean, for me at least, now I do all this electrical stuff. My home, I definitely go through and I never have any trouble updating and upgrading things. But yeah, electrical shock can cause internal damage of all different types, right? You can, oh God, basically current will travel wherever it can. The big rule of current is it will follow the path of least resistance. So if you have a pool of water sitting around, it's much easier for the current to travel through that. Your body, you're mostly made of water. It likes to travel through you. Um, yeah, wherever it can, even to the point, I mean, it'll travel. It has a given area where it could travel through the air, right? How far do you think an arc flash can travel through the air? There's actually a whole thing in that, and that's why usually in front of panels and stuff, you have a 36-inch clearance, right? Because that is how far can we, that's a safe distance. Anything within that range, yeah, it has a potential of possibly getting, an arc flash through the air and becoming energized. So yeah, current's a funny thing. It'll go where it can. Just a little, and this leads up to, right, why we need to have circuit protection. Otherwise, we would just have all this stuff hardwired, boom, boom, straight from the transformer coming in. But that would be the perfect world. In the real world, it doesn't work that way. So yeah, your resistance of your body is not very, very high. You, in fact, have not much resistance against current. And that's why I always say whenever you're working in the panel or something like that, you always try to ground your wrist out to the side of the panel. So if current were to fly through your body, it literally would only go through your hand and be grounded out. And that's the electrician rule, one hand in your pocket at all times. Because when you have two hands, excuse me, that's when you can get the current going across your body, going across your heart, stops your heart, and it does not take much. Yeah, and a rule of thumb, generally voltages less than 50 are safe. Um, and safe is a relative term, okay, because even at 50 volts, that shit can hurt like hell. Um, there's stories of people that have gotten the flash, and it's like, yeah, that stuff can hurt, and it the weird thing about getting shocked, it depends on the shock, but sometimes, I mean, it can even make your bones hurt afterwards, where you just don't feel right, and even for a couple of days. It all depends on how it's gone through your body. It can burst blood vessels. In fact, a really large, you can tell when somebody's gotten a severe electric shock, you know, because all their fingernails will turn black, and even, you know, the whites of your eyes will turn like black, where you look like some crazy vampire or something, because it's literally burst your blood vessels. So you'll live through it, right? But oh my God, it'll hurt like hell. So, but yeah, pretty much anything over 50 volts is considered potentially lethal. That, you know, not only will it kill you, but it will hurt the whole time you are dying. I mean, I try to make light of it, but the reality of it is, yeah, this is dangerous stuff, right? Always, always, always. You cannot. Let me tell you, you know, you get a rush from the boss, or some crazy manager wants you to get this fixed right away, you know, and it's like, hey, there's no rush when it comes to dealing with safety. It's like you gotta. It's one of your major golden rules. It's always, you know, stop and assess before you do. And you can't take too, well, you can't take too long, but you can't take too long on trying to make sure you have proper safety guidelines. I mean, I cannot stress it enough. So, yep, effective electric shock, right? And of course, and what can kill you in current? It's milliamps. So, you know, you're dealing even with residential. You know, what's your VA on these things, right? You pulling a 15 amp thing in there, so you have potential of 15 amps. And if milliamps are going to kill you, well, guess what? 15 amps is for sure going to kill you. um, Depending on the range of it, right? Like, okay, in this case, if you go down the list, 0.4 milliamps can't really be felt. 1.1, that's when you get like a weird kind of tingle, almost, almost. I don't know if everybody's done that little transistor battery thing on your tongue where you feel that tingle. It'd be something like that, where you feel like a slight weird tingle to something, even to the point like down to the 1.8, where you're getting a little bit of a shock, where you're like, oh, but it doesn't like hurt, just enough to, you know, give you a little alarm. But yeah, and that's the thing with this stuff. So if you go down the list, see, once we get up to a high enough range, what happens is it grabs you. It literally grabs you. And then what happens? So you got to think, how does the body control your muscles? It's all by electrical stimulus, right? So if your brain is being interrupted by you getting electrocuted, you cannot tell your body to let go. It's literally overriding your muscle response. You know, it grabs you, and that's when it, you know, somebody's like grabs and it won't let go. Yeah, well, that's because that is how electricity does it. And then at a certain point, right, you get the shock over your heart, where, of course, your heart's, again, it's controlled by electrical stimulus through your body too. And then if that gets interrupted, your heart just stops getting a signal to pump, and it just goes, oh, okay, no pumping, and boom, you're done. And it's a weird thing, but yeah, electricity, it doesn't take much, and it doesn't forgive. And I mean, you know, and the bad thing is, it's like, so if your buddy's getting electrocuted, a lot of people see, and this is dangerous as well. So your first impulse is to go and grab a hold of them, and that's like, oh no, that's the worst thing you can do. Your best thing, and it's horrible thing. I always told people I used to work with, it's like, yeah, I like you enough, I'll grab a 2x4 and I'll clock you with it. But in reality, it's true. You know, you got a nice 2x4 where it's non-conducting, and you could hit somebody off of a panel if they're getting electrocuted, or off of a wire or something like that. You know, or I told them I would drop kick them, because if you're in the air, you'll get a momentary shock. But anyway, but yeah, it doesn't take much. It does not take much, and you're done. It's game over. And we get a pretty little graph, and we see like time responses, right? How long it takes, and it's like boom, boom, and everything is over. How much it'll be. So yeah, it really does not take much. All of this is all in the milliamps. And I mean, you think about that, and it's like, wow, milliamps. It doesn't seem like much, and it's like, no, it doesn't seem like much, but it's enough. And that's why they came up with like the GFI's principle, right? The whole ground fault interrupted versus the electromechanical. Because I mean, don't think that your circuit breaker in the panel isn't going to work, because it is, but it's all about how long it takes. So the circuit breaker in your panel, a good old electrical mechanical one made, designed in 1936, it will trip, but how many seconds until it trips? And that was the problem. So those seconds are long enough to electrocute you, basically enough to stop your. So what they wanted was something that would trigger quickly, and that's where the GFI comes into place, right? So if we look in there, so it'll open from, I mean, 0.035 seconds to just less than 0.1 seconds. So you can't even blink that quick, which is precisely what you want. The minute you have that happen, boom, it shuts off and you're safe. And that was things, goofy things, especially the kitchen is so dangerous. Oh my God. Kitchens and bathrooms. Who would think, right? But, for some reason you didn't notice it, and you got somehow water got all over, and you're just going to make some toast or something like that. And the next thing you know, you're dead. And it's like, oh, that was fun. Yeah. But, that's why the GFI is there. That's why wherever there is going to be water, you want one of these things there. And that's how they specify. Pretty much that's the way to look at it. Anywhere there's going to be some type of water, then you need a GFI. That's why they say, kitchens, bathrooms, right? All outdoor stuff and everything. So if you can have water, you want one. So yeah, the GFCI, right? It's and you need it in a readily accessible area. You can't have it like mounted behind things and stuff like that, because you do have interaction at your. And those too, did you know? You're supposed to go through and once a month exercise your GFIs as well, because they too have that circuit breaker action, right? You got the test and reset buttons on them. Well, you're supposed to go through once a month and exercise those as well to make sure, there's no mechanical type failure going on with that. And remember, only one GFI on a circuit. If you try to put two in, okay, they will literally interrupt each other and the line will never go live. So, and the way they're wired, you have the line the line wiring coming in, right? Your hot and neutral, and if you looked in the back, you'll see there's two called line and load. And so the line comes in from the panel, and then the load part would feed off to regular receptacles. So on your like kitchen counter or in your bathroom, right? And that's why you'll see sometimes even mounted in the same thing with like a 4 receptacle deal. You'll have one of them is the GFI and one is like a regular receptacle. Well, that regular receptacle is being fed by the GFI, and it's protected by that. So even if that something happens to it, right, the GFI will still protect that line, and it'll surge. And laid out just like this. How many can it protect, right? So if anything were to happen on anything within that branch circuit, the GFI is protecting it. And see, even still back here, of course, you have your circuit breaker in the panel, doing its normal job. But yeah, the GFI is out there protecting all of those devices to make sure that if anything happens to any one of these, he will trip. And here we have a little different layout showing feeders going into your branches, right? But yeah, you generally, I don't know. You could do something like this. I don't know why you would do it, where you would basically have the GFI back at the panel. And technically, yeah, you could do it, right? You have it at like mount for whatever God knows reason, mounted in your garage and feeding off to your kitchen or whatnot. I mean, as long as that individual line is protected by the GFI, you're allowed to do it, but it just would seem odd. Usually they're mounted and, like in the area they're servicing, so like in the kitchen or the bathroom or outside or whatever. But yeah, but technically you would be allowed to have it mounted at or near the panel if for whatever reason. I don't know why. But yeah, we look at and it's an active device, right? So the original circuit breakers were what they call passive. There's no um, controls to it or anything. You don't have to adjust anything. It's electromechanical. It works as it's intended, as it's rated, and basically it just reacts. Now GFI, he has actual circuitry inside of it, so and that's why they tend to be pricier, right? Because and hence the size of it too compared to a regular receptacle is you actually have active circuitry involved in that that literally is sensing or monitoring the current, and that's why it has such a quick response time to it. Excuse me. So yeah, it looks at and like the video demonstration shown, it looks for differences in the current, right, both in the line and in the neutral, and they should be a fairly even balance over a given portion of time, and it senses. So and as you're running devices and this and that, you plug in the hair dryer, you plug in the toaster, the coffee maker, it's going to use electricity, so there is going to be some variance going on, but it's looking for a consistent, you plug something in and it's got that initial bounce to it, and then everything settles and equalizes. But when you get the case where it's shorted, like water or whatnot, right? That's what it's looking for, because now it's extending a little too long, and it goes, nope, I'm out. And I mean, it's a fairly easy principle, but yeah, they do have active circuitry to them, and that's why a lot of them these days have like a little green LED on them to tell that they're functioning or working, and that's why you're supposed to exercise them regularly. So if you go and press the test button and then you go to hit a reset and nothing happens, well, chances are your GFI life has just ended. And it happens, especially because you got to think it's actually got, electronics involved in it. There's an actual little circuit board into this guy. So over a given amount of time, yeah, I would expect it to fail. Everything's going to fail eventually, right? And this one even sooner, just because of that active circuitry involved. But I like the ones with the little green LEDs, because they're always, you can always just look at it, see the green LED when that's usually a good condition and a good judge of whether this thing's still working. And if it stops, you run down the hardware store and get another one and replace it, But but yep, you can wire them to protect your downstream receptacles. So that way you can have a few receptacles, like in your kitchen counter area, back more than anything, because that's where you usually have more devices, especially this day and age. We have a lot more toys than we used to. But yeah, they all have a test and reset button now, and they have what they call in the top bullet item the feed through feature, and that's what I was saying with the line and a load. So you go in the back, and I mean, they look similar to a receptacle, right? But you'll literally see in the back where the upper portion will be labeled line and the bottom portion will be labeled load, and they're separated. So the line side is literally where you would come from the circuit breaker in the panel and wire it up into that, and then the load would literally feed other receptacles down the line, and that way they get protected by the GFI as well. Yeah, like in this is a good example of it. So the original one, or our original line, see here, coming into the power source, going into the line side of the GFI, and then the load side is feed through to the other two receptacles further down. And that's how you do that, where like, a lot of times your kitchen cabinet, or even like the garage and stuff like that, where you're going to have like multiple receptacles. Even the bathroom, I wouldn't expect as many in the bathroom, but you never know. In this day and age, you might want for women's vanities or something like that. I need multiple receptacles. But there's a very typical, and I mean everything before the GFI, like these two devices here, are not protected by the GFI, but everything after on the load side here is protected. So that lumen and that receptacle there are both protected by this GFI, but before that, these two lumens are not protected by it. And that's kind of a typical, you know, it depends on who knows your situation, if you're adding in later on or something like that. But that would be a very typical layout for a GFI. Yeah, and always look in the back. I mean, you know, don't assume. It's very, very clearly labeled. It'll tell you line and load, and it's like one portion, the other portion, and they are broken away. I mean, even the screw terminals on there cannot be matched up unless you actively did it. For why, I wouldn't know, but but otherwise it won't operate correctly. It won't be able to detect that unbalance. And if it's not wired correctly, I don't want to say 100%, but usually what'll happen is if it's not wired correctly, it'll sense that imbalance and trip and eternally trip. And that means something is wired wrong somewhere, and it's letting you know. But yeah, you need to test these. They do need to be tested, and even to the point where like let's say you've been working in like a warehouse or a factory or something like that. A good, this is a lot of places don't do it, trust me, but a good maintenance PM, that would be part of the thing as well, is literally go around like the whole plant or warehouse or whatever, right, and test. And yeah, it's a horrible PM, boring as hell, but you know, it has to be done and make sure that these things are working correctly. But a good maintenance PM would be going around and testing your GFIs on a periodic basis. I mean, I would designate once a month, right? Go flip all the breakers in your panel, and then go out and click and check your GFIs, make sure they're working, and you know, have your own little home record, if you will. But yeah, a good maintenance routine literally would have that, where you are periodically going through and testing, even to the point of circuit breakers, you know, on and off, all the way down the line. You know, they have, I know some places go, you know, where they operate the 24/7, but they do have like, most places have like a maintenance shutdown. One place I worked for, we called it was like a 2-week shutdown, where they would go through and do all the crazy maintenance projects that they couldn't do while running, because they literally ran 24/7. Yeah, we called it the hell 2 weeks, because you were literally, it was like everything that was building up on the maintenance list, now I had to be gone through and done over those 2 weeks of time. But you had great overtime checks and stuff. Like, oh my God. But this would be that time, you know, a good maintenance thing would be, okay, run through the list here, go flip all these and check them and all that kind of thing. But anyway, and now we get into, and if you heard from that Eaton video, right? These are new, well, not new, but from 1994. So this is the newest kid on the block, the AFCIs. And there would be no reason not to have these. It's an interesting looking circuit breaker. It looks like a circuit breaker on steroids is what it looks like. It's got active circuitry inside of it, so it tends to be, it'll be longer, because you can't be bigger up top, right? Because you got the panel mount, and it's got to be flush. So as far as space requirement, it'll still fit in, you know, in a proper circuit breaker path. But you'll notice it has like down here, that is much longer for the circuit breaker, because it does have active circuitry in there for the arc fault protection. And these are, I mean, for AFCIs, you wouldn't really put them on lighting. You know, you wouldn't have anything. I mean, who's plugging extension cords into the light? I mean, I guess anything is possible, of course, right? But on a typical thing. But yeah, I would I would expect these to be on regular receptacles throughout the house. I mean, you have to take it. They are costly. They're not costly, but they are more expensive than your average circuit breakers, right? But again, what's your value on, whether your house burns down and kills you and that kind of thing. But and you can get them, and they do have them in the two styles. I have seen them in the receptacle style like this. That would be more of an add-on, or if you just want specific receptacles to the house protected, you could have it that style, or protect the entire branch. So you feed your front room or something like that, where you're going to have a lot of extension cords and a lot of plug-in things like lamps and vacuums and whatnot. Yeah, it would be a good rule of thumb to go through and install these bad boys. And they have like an extra sense line to them, so they're a little strange looking, but they fit right in there and everything. Like I say, they're just longer, so they do tend to take more space to them. But yeah, and I mean, the AFCI doesn't have really a rule to it per se, like the GFIs do. Like, GFIs are going wherever there's wet because they're protecting against that. AFCI is more of what do you feel comfortable with protecting, like what areas, that kind of thing. So you do have to think about like what you're going to install it on and that type of thing. Like I say, the front room, high active areas where you're going to be doing a lot of plugging in and out with, like I say, the vacuum cleaner and things like that, where you're going to have extension cords on a regular basis, that type of thing, then this would be a good rule of thumb to go ahead and put AFIs in there. But yeah, arcing is considered one of the leading causes of electrical fires, and it's extension, well, not extension cords per se, but cords. You got these cords, and like I say, over time they get abused, they're old, who knows what, but for whatever reason, that insulation has gotten compromised, and now you've got these little, and I mean, you can see it on some of these where you can literally see the little arcing occurring across like this whole cord. I've seen it a couple of times, and it's not quite enough where it'll trip the breaker because it's not staying consistent, but it is enough where if it was like on a carpet area or behind, flush up against the couch or some kind of fabric or something, it'll light it up. And the crazy thing is even when it's, the burning thing, until the insulation, of course, is burned away, that circuit breaker won't trip. It'll continue to feed that. So you'll still get this arcing happening. And yeah, next thing you know, your front room's on fire. But yeah, all kinds of areas, right? High active areas where you're going to have stuff plugging in and out and whatnot. Your family rooms, a dining room, living rooms, parlors. I don't know. I don't have a parlor, but a library in your den. But depending on your house and your situation. But yeah, anywhere where there's a lot of activity where you plan on having extension cords, not a bad idea. Yeah, and they got combination ones. Which are kind of weird. You can get like like I say, the ones that are back in the panel that'll protect the entire branch, or you can have like the outlet ones, right, where you're installing it in with the receptacle mounts and installing them in individual spots. It's all on what you're comfortable with, I guess. If you feel that the branch one is overkill and whatnot, yeah, you can go around and do individual receptacle style ones. Yeah, it all depends on the placement, how the things in a house are getting used and that kind of thing, and the cost factor as well, of course, right? But again, what kind of cost is there in burning your house down? But anyway, so you guys have run into this little term at this point, right? Tamper resistant. And what does that mean? Well, tamper resistant means that it can't be accessed from the outside. You don't want anybody, especially like little kids and whatnot, being able to get at live voltage and stuff like that. And so what they have on these new ones, it's hard to see in this, but where the spades insert in there, there's actually like a nylon sleeve that has like a spring action to it. And so it literally will stop. So if you try it inserting, like let's say a little kid comes by and tries inserting something into the one side but not the other, it won't open. It literally needs both spades being pushed in simultaneously for it to swing open. It's almost like a little trap door. So yeah, if a little kid or who knows, your pet, I don't know why a pet would, but you never know. But we're trying just to stick something into just one side, yeah, it won't open. It needs contact on both. So these are a newer style. You can look and see into your house if you have these type of receptacles or not. It's literally like a nylon sheet, like a little guard that's in both of those. But yeah, that's how it works. You can't, if you try installing something on one only, it will not open, and that's, yeah, tamper resistant. And it's a nice little device. It really didn't jump the cost up on these receptacles at all. So there would be no reason why you wouldn't just go out and buy these ones instead of, the other style, just because of the safety factor involved with it. But yep, that's tamper resistant. So, and they do have codes on this, right? So if we looked up in 406, section 4, um, they have like for replacements and things like that, what you're required. Because, all right, so let's say you're doing, older style homes and stuff like that. Like I said, where you didn't have a ground, you can't buy those type of receptacles now. They have that ground connection there, but let's say you go in there and instead of doing like a very costly wire repull, right? Especially if we're dealing with the sheath style wiring, the Romex. Because if it's the old style where it just has the 2-wire, you would literally have to repull the whole thing in order to get the 3-wire in there with the ground, right? Or try to somehow crazily run a ground wire to this thing. So you are allowed to replace 2-wire ones where you don't have the grounding capabilities, or you do have the grounding capabilities. So if you do have the ground, go ahead and attach it, right? And that would be a good rule of thumb. But if you don't, and you have that new style, so now it's got that ground plug on there, so that's like falsely identifying is the way they look at that. So you got to watch that with that. So what they say is you have to clearly label that there is no ground. Yeah, see on the far left here, that's the old style, which you'll still see in some homes, but there's no ground to it. That's the one where people will come by, grandpa's gone and ripped the ground prong off of his vacuum cleaner and plugged it in anyway. But yeah, the new style, of course, we have the 3 prongs, right? So it's got a ground attachment to it. And again, you might even have like the old wire where there's literally in the box just the line and the neutral. So then you would have to basically run a whole grounding wire, which can be done. It depends on the situation. Sometimes there's certain areas where maybe without ripping the whole wall apart or something like that, and the homeowner doesn't want to do it, that kind of thing. So, but if you do, yeah, you would have to label it that says, your new device does not have a ground on it. Otherwise, yeah, you're allowed to replace the devices. Or at the bottom one, you can install a ground. But yeah, that's the old style where they would have just had the 2-wire gone in there. I think some of the ones from my grandma's house were like that. It was like an older, but yeah, what do you do, right? So surge protection, which is a little different. That's actually that's relatively new as well. And it's an active circuitry deal, and you get surge protectors. They like to use them for especially like sensitive devices like computers or even some of your high-end electronics and stuff like that. In case there's any kind of weird surge of any kind, it literally has active circuitry to protect against that. So that way, for whatever reason, I don't know, your power is going on and off through the house, there's some storm or something like that. But if you were to have it continually arcing like that, eventually that on and off motion can send current spikes down your line. And so some of your devices, especially like computers and whatnot, they're expensive as well, but they're susceptible to that kind of thing. And if it's occurring too much, yeah, those current spikes can literally damage electronics. So they have surge protection devices, and this is like active componentry, right? Where you literally have, well, yeah, you can have a whole house surge protector. That's fairly costly, but people do it. More typical styles are, these outlet ones here, where you would have that going up to like your computer station and that, or even to the point where you might have it up to your plasma TV or something like that as well, just protecting your electronics. And believe it or not, yeah, this strange little guy down on the right, they actually make receptacle surge protectors that you can buy. Not many people know these exist, but yeah, notice the identifier on it. It does have a test and reset similar to the GFI, but they identify it differently so people wouldn't confuse this being, oh, that's a GFI, and it's like, no, it's not. It does a different kind of job, but yeah, you are allowed to, you can do this, but commonly this is usually what they have is like receptacle strips, right, with a little reset button to it. It has fused, if you will. But and yeah, they do have them where you can get the whole house protected in, even to the point where your telephone and like cable and stuff like that all run through it, so it's not getting spikes as well. Because believe it or not, if you're and some of that stuff like your TV, right, your or even your phone, again, it's wire, so it can transmit. But if it got some crazy spike where it normally isn't supposed to, that could cause damage to your electronics, which is crazy. But and that's what these things protect against, right? So that's just another type of protection you can commonly find in your home. But yeah, not many people know that the receptacle version exists. In fact, I don't know if I've ever, outside of being at Home Depot and seeing, I don't think I've ever, I know I've never installed one of these receptacles myself, but it wouldn't be, if you had like a dedicated computer station or something, or even for your television area or something, wouldn't be a bad deal, right? All right. So operational arcs, what is it? Well, you turn the device on and it's got an instantaneous rate of charge, meaning it's going to pull more current when it's first turned on, powering up, and it's going to rise up. So if you were to monitor your current, let's say normally the thing pulls 5 amps, okay? Now, when you first fire it on, it could rise up like 30 to 50% over that, where your 5 amp device now is shooting up to like 7, 8 amps, right? And it's instantaneous rate of charge. It settles down once the thing's running, typically with motors, because you get the coils being involved, but lamps as well. Anything where you're energizing, yeah, it has instantaneous rate of charge, is what they call it. And it has a settling time, and that's why these usually don't trip circuit breakers in your panel, is because the time involved. By the time, of course, the circuit breakers monitor to see if it's going to be a problem, but usually it settles down. Like I said, if we were to watch it, it would spike up, hit a peak, and then settle down and have like a couple of bounces until it actually plateaued out, and now that the device is charged properly and running properly. But yeah, typically motors, anything with electromagnetic, they're going to spike pretty high. But even to the case of like a lamp when you first turn it on has that as well. And that's why in some cases, you in the old, especially the old style light bulbs, when you first turn it on, if the filament's weak, it blows out. Well, that's because of that current spike hit it, momentarily. And if the filament was already weak, well, it's gone. But usually that's when you see that, right? You'll turn on the thing and boom, there goes the light bulb. And it's like, damn it. But that's why it happens. Because when you first turn it on, that initial pool of current. But yep, here's a cutaway of the AFCI. And you can see in the front part, it's very much like the old styles, right? Where you have the typical circuit breakers with the spring. You got the little copper braid in there, electromagnetic functions right through this, right? But now we go over here and look at that. We've got a whole active circuit board where this thing is literally, like I say, this is an active device versus the passive device. Because like on the right-hand side here, that's passive. It's waiting to react. This one, it's reacting all the time. And that's your difference between active and passive, right? Waiting to react and then no react. It's constantly there. In fact, it's looking to react. But yeah, it looks for that. And like I said, it's a great thing, especially, I don't know if anybody's remembers that older movie Christmas Story where the father had like and that was old style homes back in like the 50s or 60s, right? But he had like little extenders for his receptacle where he had so many different things plugged in on one and it was sparking off and whatnot. And didn't think anything of it. But yeah, you got to protect people from themselves because they can be dangerous. Yeah, we're not, oh boy. Sadly, we won't be doing it, but we would have gone through and done like some lab work with all of this. Excuse me. Not a typical layout, but yeah, we won't be looking at that. But that's pretty much it. We can, if you guys want, hold on here, if I can find it. I don't know if you guys have ever, let's see if I can get this guy. This guy makes a lot of money by doing these videos and stuff, and I don't know if anybody's. Oh.
Hi, I'm Rex Moore with the Motley Fool
I gotta get through this commercial.
BMW's self-driving.
Hi, I'd like to talk.
So, yeah, this guy Mehdi, if you ever do lookups, he does a lot of electronic, like testing, if you will, but almost in a way where like how not to do it. But it's kind of an interesting, let me see here if I can pull this up right. Hold on here. Oh, wrong one. Yeah, he does a lot of like electrical testing, but oh my God, the way he does it is, it's too funny. You guys can see that okay? They also call him Mehdi the unibrow guy.
I can see it.
Huh? You see him okay, Jared?
Yeah.
All right. It's just I don't know if we'll watch the whole thing, but he goes through and actually does like how a GFI and AFI work kind of thing where he does like, well, we watch the video. It's kind of funny. If you've never watched this guy getting an electrical, yeah, this is his name here, Mehdi. You can also type in like Mehdi unibrow because he's got it trimmed here, but on some of the videos, he definitely has a really pronounced unibrow. So
GCIF, no, ground fault circuit interrupter outlets. They are typically installed in washrooms and are an essential safety feature. In my last video, I talked about this girl that was electrocuted in the bathtub because she accidentally touched exposed wires. This would have saved her. Unfortunately, her frayed extension cord was not plugged into a GFCI outlet. You can watch my previous video about it. Now I will demonstrate to you how this outlet saves lives.
Is this the end of the lovable idiot?
Well, before I put myself at the mercy of technology. Let's test it differently.
What the GFCI outlet does is that it senses the current. Any current that comes out of the live wire must return to neutral to close the circuit. If it comes out of the live wire but doesn't return to neutral, it means that it's going to earth through an unwanted path. The outlet would open its breaker right away to avoid the unwanted current flow.
So if you're sitting in a bathtub full of water and you drop a toaster in it, the current would go to earth through the faucet or drain plumbing that are shorted to earth. The outlet would cut the power right away and save your life.
Okay, let's test it out. It says test monthly. There's a test button, okay? And the red light is off, so it's all good. Now, if I plug in my wire and short the live, which is the black wire, to the earth, which is the green, the breaker should pop. That wasn't the outlet breaker. The whole washroom breaker popped.
Okay then, if it's a dead short, the room breaker opens quicker than the GFCI. Now let's measure my body resistance. It's around 300, 400K. So if I put a 330 kilo ohm resistor between earth and live, I suppose the breaker should open. This is a 330 kilo ohm resistor. Nothing. I guess I will be dead. But wait, human body also has some capacitance. Mine is around 4-5 nanofarad. Let's say that also doubles the current. So I guess if I use a 100 kilo ohm resistor between earth and live to increase the current, this should pop. Nope. I guess I will be dead again. What's the current threshold? Trying 56 kilo ohm. I will be certainly dead, I think. Okay, trying 10 kilo ohm. Oh, it popped. So that means 120 volt AC divided by 10 kilo ohm is 12 milliamps. What the actual, that's a very high and dangerous current. Okay, I bought this GFCI outlet so I can try it outside the washroom. And I connected a potentiometer between the live and earth to see exactly where it will trigger. We don't short anything. High voltage makes me nervous as Let's check the potentiometer resistance. Pretty much 24 kilo ohms, which means 120 volt AC divided by 24 kilo ohms is exactly 5 milliamps. So these things are designed to trip at fault currents of over 5 milliamps. Again, it doesn't pop if your body is between live and neutral. It will look like a normal circuit. It only pops for currents over 5 milliamps between live and earth. I think 5 milliamp is a pretty high and dangerous current, but according to information, you start sensing electricity around 1 milliamp. I personally start sensing it around half a milliamp. 1 milliamp is pretty painful for me. As it goes up around 10 milliamps, it becomes extremely painful and can cause severe shock and muscle paralysis and death. 10 milliamp and higher, you won't be able to let go, which results in extended exposure to electricity that would result in death. Closer to 100 milliamp, it becomes very hard to breathe and there is irregular heartbeat that would easily end your life. Above 100 milliamp, you die. Breathing stops completely and there will be severe burning as an added bonus. Of course, all these depends on the length of exposure to high current. For example, in case of a 25 kilovolt electrostatic discharge, the current through body is way more than 1 amp, around a microsecond, but that doesn't affect a healthy person. But if it's a fixed high voltage supply creating high current, you won't be able to let go. So according to this, 5 milliamp is quite painful but not lethal. And with my body impedance of over 100 kilo ohm with 120 volt AC across my body, there will be only 1 milliamp of annoyance. So does that mean that I can grab power lines with dry hands with no consequences? But I know that if I touch live wires, I'll die, I think. So there should be a disconnect somewhere. Okay, let me check my body resistance and impedance. I'll run some current through my body using my DC 30 volt as well as 60 Hz 30 volt AC coming from my auto transformer. Dry hands 30 volt DC. Around 0.1 milliamps. Dry hand AC is 0.14. Wet hand DC is around 0.6 milliamps. Wet hand AC is around 0.8 milliamps. Soapy hand DC It's around 0.8, 0.9 milliamps. Soapy hand AC, 1.3, 1.4. Tongue diesel. Tongue is very low resistance, so the current would be higher. Let's measure it at 3 volts. Okay, tongue at 3 volts. 0.4 milliamps. And AC 3 volts. Oh, 1.7. I don't get it. The GFCI breaker would hardly open even if I'm soapy, but I should die even if I touch the live wires with dry hands. Let's experiment a little bit with water. I have cold tap water, hot tap water, and soapy water, and I'm going to put the live and earth wires in each one of them to see which one triggers the breaker. Starting from cold. This one doesn't trigger. Hot water. Okay, that one pops, which means that there are more chemicals in the hot tap water, so don't drink it much. And now the soapy water. Well, definitely. So good news, everyone. If you're in a warm shower and you drop your hair dryer in the water, the breaker pops. Let's measure the resistances running some current through them with my 30 volt DC. We know any resistance below 24 kilovolt triggers the breaker. Cold water, like around 1 milliamp, so 30 kilo ohms. Hot tap water, 1.5 milliamps or 20 kilo ohms, so it triggers. And the soapy water is around 30 milliamps, which means around 1 kilo ohms. So I guess the lesson is always shower with warm water and add soap for additional safety, and make sure your hair dryer only falls into the water. Does this mean that Madison would not be saved even if there was a GFCI outlet? According to the report, she was in the bathtub and accidentally grabbed the exposed wires of a broken extension cord. According to my tests, wet hand, even soapy hand, hardly triggers a GFCI outlet. But then again, the currents wouldn't be in lethal levels anyways. You must be missing something. Let's try again. Different voltage and current levels may have different effects. I have my 30 volt AC here, and I wet my finger and measure the current through it. You see the current is dropping. It would save me. Basically, the electricity is removing the moisture from my skin and making it more resistive. Okay, let's crank it up all the way to 120 volts. According to my tests, over dry skin, it should only result in 1 milliamp of pain. Okay, let's try it. Of course, this is very dangerous. Never try this at home, okay? I only touch it with one hand, and the rest of my body is isolated from electricity, so the current is limited to one hand. Support my channel at patreon.com because my family could use the money after my demise. It's dry, right? The current can't hold it steady, too painful. Let's reduce the voltage a little bit. Okay, let's do 100 volts. Ready? Should be less painful. Okay. Ouch. What the is the current rising? Ow! It seems like at higher voltage and current, the skin doesn't limit the current anymore. It is failing one way or another, and its resistance is dropping, increasing the current. Yeah, Madison would have been saved if her extension cord was plugged into a GFCI outlet. Her skin had already failed. She had burn marks on her hands. The current would be high enough to trip the breaker. Now let's do the real test. Does the GFCI open and save me? So I have my dry hand, GFCI, and the wire. I don't think it will open because it needs more than 5 milliamps, unless my skin breaks, which I don't think it does before I pull my hand back from pain. So let's try it. This is nothing for me. Doesn't open. Never ever try this at home. I'm doing a fully soapy hand to give it the best shot. Otherwise, there will be a hell of a pain. Okay, come on. Sorry, guys. The pain is too much for me, but I'm sure it will.
It opened. It opened. Install GFCI in bathrooms, people. Giveaway time. For my viewers, I opened the T-shelf. Open.
Anyway. So yeah, if you never watched him, he's got a lot of videos on all kinds of different topics where he tests different like electronics and electrical things, but usually he ends up getting shocked because he's kind of an idiot, but that's his whole thing. I think he's got a lot of subscribers. I know he's got to be making actually some good YouTube money from his channel, but anyway. So yeah, if you ever want to watch and he's got, like I say, he's got both electrical and electronic sides. So if you're interested in either one, you can go through his channel. He's got a ton of videos out there now. But yeah, almost all of them end up with him getting like electrocuted in some way or something. But it kind of showed how the GFI works, you know, the idiot approach to it, I guess. But, and that's pretty much what I have today. You guys have any questions? We're doing good with everything so far. Is this making sense? I mean, you know, a sad thing, usually I have you in my classroom, so I always talk with everybody a lot. That's, you know. You could talk. It'll let you. No. Yeah, we'll be going forward. You know, chapter 7 will be our next venture here, and looking at this. And like I say, it's pretty much, you know, my goal is to get you through most of the stuff for home wiring. You know what I mean? So all the common things. Like, we will not get through this whole book. The great thing is I would, you know, especially, I hope you bought the textbook, because I like the thing. It's just a great reference, you know, because the way it has the pictures with stuff and how to do things and things like that. Because if you're not doing stuff on a regular basis, you know, even if you knew it, eventually, you know, with anything, you get a little rusty, and it's like, oh yeah, wait a minute, I need to check that, you know, that kind of thing. And that's why I do like this book a lot. But you know, and a good thing, like I say, with building prints, and you know, it's not something that goes away if you're doing any kind of electrical, because you're always in a building. So whether it's a warehouse, you know, store, house, you know, the building prints, they use the same symbols and stuff like that for each type. Granted, you may know the population of things like in a warehouse or a factory compared to what you have in a house is going to be quite a bit more. But you know, usually like the last place I worked at, they had their building prints. I think we had, I don't even want to remember. It was I don't know if it was 100 pages to it, but there's a lot of pages. Whereas, you know, like the home prints that we have, what do we have, 10 altogether? So 10 pages of prints compared to like a factory where you have, you know, just tons and tons of building prints. But again, it's always the same, you know, symbology as far as that goes from each to
oh, here we are. We back at it again with another challenge.
What?
Sorry, my brother was trying to show me something. I don't think he realized I was on class.
He's podcasting. I taped him. Yeah, I was wondering. I'm like, okay, wait a minute.
I just walked in the door with a video open on his phone.
Nah. But yeah, you guys have any questions, or we're going okay so far? I mean,
everything's all right so far, at least on my end.
All right, we're not struggling with none of this. I mean, I don't think it's, you know, like I say, some of the formulas, yeah, they can be a little weird in the beginning and stuff like that, but you really, I mean, when you get down to it, it's always Ohm's law. And a great thing, like I said, with their Uglies book, you know, you always have that stuff listed in there. You just have to, you know, apply which one you're dealing with, single phase or three phase. because it's pretty much your two types of system, right? Single phase, three phase, and they even go through, which is kind of cool. And I don't know if I have a demonstration, but doing like delta versus Y. And basically, I mean, a way to look at it, if you do like a delta or a Y, the Y style transformer hookup, if the reason it's done in a Y, if you look in your Uglies book, is you're allowed to center tap, and that's where you get the neutral involved. Okay, so most homes are done in a Y conversion style. Now you get into some of these like factories and stuff, you know, Caterpillar or whatnot, right, where you're dealing with three-phase power. A lot of times there'll be a straight delta configuration where there is no neutral. You have 3 hots and that's it. 3 hots in the ground. And then where you would have situations where you would have to have a neutral and whatnot, you know, like offices and meeting rooms and break rooms and that kind of crap. They literally inside the plant will have transformers there, you know, usually sitting in some kind of excuse me, gray bin box of some sort, different sizes depending. But yeah, I'll tell you what, you haven't lived until you've had one of those open, and you're going in and testing it. You know, I've had all my lineman clothes on and everything, and you go in there very carefully with your probe, and that stuff, because with that transformer wide open like that, I swear to God, it's almost like all the hair on your whole body stands up. Even hair you didn't know you have, it's standing up on your body. but yeah, but yeah, the Uglies book even has that, you know, and how to even do like delta 2Y configurations and vice versa, which is kind of cool. But yeah, usually you're dealing with single phase. You're dealing with the Y conversion because you get the neutral coming in, that kind of thing. Then if you have like a lot of time the 3-phase, although 3-phase can be done in a Y conversion as well. It all depends on, you know, what the requirements are, but later on you'll get more into that kind of thing. But yeah, if you look in the Uglies book, it's always single phase, you know, 120, 240. And then one of the fun questions they always ask yourself, and it's like, well, you go through the house and you never, ever, ever measure 240 for some reason, right? You always deal measure 208, and it's, where does the 32 volts go? But, and it's an RMS thing. You actually do have, because now you have 2 different phases happening, so you have a fair amount of voltage loss on the peaks. Yeah, it's one of those, I don't know, just a little trivia things. But anyway, but now we're going into chapter 7. We'll learn some more stuff. You know, we get into like the neater devices. Like I like chapter 6 just because it looks at, you know, the different devices like that. You don't even really realize, it's like, oh, how do these things work? And it's like, oh, okay. Even to the point, like I say, that surge protector receptacle, I have never installed one of those in my life, but it wouldn't be a bad idea for certain things, I guess. But there you go. Yeah. Well, I guess then I will meet with you guys on Thursday, and, you know, get in touch with me if you need something or whatever. I'm always approachable. We can do nothing set in stone. Our main goal here is to try to learn this stuff, and that way, you know, we're ready for some entry level, if you will. Get us ready to be apprentices out there. And that way you have some knowledge to go in with. That's what they usually want. And just remember, later on down the road, I mean, this never stops, which is like say, the good thing about having this book, you can always refer back to it. The only thing that happens over time, of course, you know, it doesn't, you know, if you have like the 2017 NEC and 10 years from now, right, your NEC has changed and whatnot, but still a lot of the principles will still be there. Just have to keep in mind what changes may have occurred. And that's a cool thing. Once you get familiar with like one version of NEC, they do, when they do the updates, they also publish like what the updates or what the changes were. And so your primary thing, right, is looking from articles 100 to 400, because that applies to everybody. So the 100 to 400, that would be the ones you would want to keep on top of. And then anything you might specialize in. So depending, like if you become an HVAC guy or something like that later on down the road, then the further articles might apply to you. Like if you getting articles 600 to 700, 800 or whatnot that are specific to your field, and that would cover that. But yeah, and then I mean, and with that, anything, NFPA does a lot. They do a lot of fire protection stuff. They not just for the electrical world, but they have like mechanical versions of things, all kind, basically anything that could catch on fire, they have their fingers in it. And so when you get out there, the thing to remember, it's not just the NEC, but NFPA. And if it's in the 70s, NFPA 70 anything is electrical. And electrical. Now, if it's in the 60s, that's non-electrical. 80s, non-electrical. But 70s, yeah, it's electrical, and they have different numbers for it. There's like one range is for actual like electrical inspectors. They have their own NFPA deal. The NEC has its, and then the specifics like for certain areas, machines. So if you ever want to look up like I don't know, if you end up becoming like a machine electrician, you do a lot of CNC stuff, rebuild and all that kind of crap, then NFPA 79 has a whole deal for you, like proper wiring for machines and that kind of thing. But yeah, they got a lot of, NFPA does quite a bit of stuff. But yeah, always in the 70 ranges, that's electrical, that pertains to you. And then the NEC, like I say, anywhere from the 100s to the 400s is for everybody, always, at all times. And then the later ones are more job specific, depending on what you get into. So, but anyway, I'm just talking. This whole stay at home thing, I'm telling you. But anyway, but yeah, if you guys have any questions on any of this, like I say, we're doing chapter 7. We'll get into that, and then any questions on any of the homework or any of the work that we're going to be doing, just let me know, and then we'll go from there. If you get that worksheet in, because that is a graded, it's one of the few labs we're doing, unfortunately. But if you're having any trouble with any of those calculations, I know the one section we're not going to be able to do reliably because I don't have the electronic NEC book, but you should still be able to size your raceway, what your service entrance is going to require and all that kind of thing. And I don't grade hard on it, so depending on how your calculations work, but let me know. And like I say, you can always extend dates and things for homeworks and all that. I mean, I didn't think I'd put too many questions into each one. There's only, what has the most been, about maybe 10 to 15 at the maximum, I think, questions, but I don't know. I think it's the more important ones out of each chapter. So, but yeah, if you guys don't have any questions, that's about it for me. And we'll see you guys on Thursday, right?
Mr. Brown,
Yes, sir.
make sure to keep your eyes open. I'm going to send you an email about, so I just got, my job called me back in for next week to start doing part-time again.
Okay.
So I'll send you the details on what they're wanting me to do. I don't think I'll be able to attend Zoom meetings as of next week.
Oh, that's okay. I mean, well, I tape them, and I put them up on, like for each day, I get them down so you can always review them, or I always have just the PowerPoint slides on, the day tabs too, if you just want to look at the PowerPoints and that kind of thing. So, but all right. No,
yep. Just wanted to make sure you knew. And then I'll send that email so that way you've got it in like a digital copy.
All right. Well, no, thanks, Nathaniel. Yeah, I'll keep my eye out. And yeah, you got my email address, and
Yep.
All right. All right. Well, good, I think, right? Getting work is always a good thing.
Oh yeah, especially in this time.
Yes, it is. Well, good. Congratulations.
Thank you very much.
All right. Nothing else from you guys? Is that it? We're gonna go ahead and I'm gonna stop recording here. I think.